You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The purpose of this episode is to anchor your study with a clear vocabulary of data and platform concepts. These terms are more than definitions. They frame the way you think about classification, protection, resilience, and compliance. Cloud security depends on consistent language. When teams use the same terms with the same meanings, controls can be selected, applied, and audited with precision. For CCSP preparation, these words are not just exam content, but the grammar of cloud practice. Misunderstanding them risks confusion in both test scenarios and real operations. This glossary session builds fluency, so that when you encounter complex case studies or professional conversations, you can move fluidly from lifecycle to encryption to resilience without hesitation. A shared vocabulary ensures that your technical reasoning rests on a solid, unambiguous foundation. The data lifecycle traces information from its creation through to its destruction. Stages typically include creation, storage, use, sharing, archival, and eventual destruction. Each stage brings unique risks and corresponding protections. At creation, data may need validation. In storage, encryption and access controls protect it. In use, monitoring and access restrictions apply. In sharing, governance and compliance obligations matter. In archival, retention and immutability rules apply. And in destruction, secure wiping or physical disposal ensures confidentiality. Understanding the lifecycle keeps security from being one-time and instead embeds it across the full span of data's existence. In exam questions, lifecycle references signal scenarios where protection must adapt to changing states and uses. Data classification assigns categories such as public, internal, confidential, or highly sensitive. Each class carries handling requirements, from who may access it to how it must be encrypted or logged. Classification creates clarity, allowing organizations to apply scarce security resources where they matter most. For example, encrypting every single file may be impractical, but ensuring encryption of sensitive health records is mandatory. Classification also supports compliance, since many regulations require evidence of structured handling. For CCSP candidates, knowing categories and corresponding protections prepares you for scenarios where prioritization and governance drive decisions as much as technical controls. Roles around data provide accountability. The data owner defines how data should be classified and protected. The data steward ensures policies are applied day to day, acting as a caretaker. The data custodian manages the technical infrastructure, such as databases or storage, where data resides. These distinctions prevent confusion. For example, a system administrator may configure permissions, but it is the owner who decides whether the data is confidential. Exam scenarios often highlight these roles to test whether you can separate authority from execution. In professional life, clarity around these roles prevents gaps in responsibility, ensuring both governance and technical protection align. Data residency and data sovereignty are related, but distinct. Residency refers to the physical or logical location where data is stored, such as within a specific country or region. Sovereignty refers to the legal authority governing that data, which may extend across borders depending on laws. For example, data stored in one country may still fall under the jurisdiction of another due to ownership or treaties. These distinctions matter for compliance with frameworks like GDPR. For CCSP learners, questions may test whether you recognize that location alone does not define legal obligations. Sovereignty can extend beyond residency. Structured data is organized and stored in defined formats, such as relational databases where fields and tables enforce order. Unstructured data, such as documents, images, or videos, lacks this predefined structure. The difference matters because structured data is easier to query, analyze, and secure with traditional tools, while unstructured data often requires advanced processing and may contain hidden sensitive information. Cloud environments must secure both types, but strategies differ. Exam references to structured versus unstructured highlight these distinctions and the implications for classification, searchability, and protection. Object storage is designed for scalability, durability, and metadata-rich access. Each object consists of the data itself, metadata, and a unique identifier, making it well-suited for massive, distributed environments. Use cases include backups, multimedia storage, and big data analytics. Security considerations include access controls, lifecycle policies, and encryption at rest. Object storage exemplifies cloud-native design, flexible, resilient, and cost-effective at scale. For CCSP candidates, object storage terms signal scenarios where scalability and metadata management are key. Block storage, by contrast, delivers fixed-size chunks of storage, typically attached to virtual machines for transactional workloads. It resembles a traditional hard drive, offering low latency and high-performance characteristics. Databases and enterprise applications often rely on block storage for reliability and speed. Security considerations focus on encryption and consistent snapshots. In exam terms, block storage scenarios highlight needs for performance, transactional integrity, and fine-grained control. File storage provides a hierarchical model familiar from traditional file systems. It supports shared access, directory structures, and permissions aligned with user groups. This makes it useful for collaborative environments and applications that expect traditional file protocols. Cloud file storage extends this model with scalability and distributed access. For security professionals, file storage often intersects with access control, ensuring permissions remain consistent and appropriate across shared systems. On the exam, file storage highlights traditional patterns extended into cloud contexts. Consistency models describe how quickly updates propagate across distributed systems. Strong consistency guarantees that once data is written, all reads return the latest version. Eventual consistency allows temporary divergence, with updates propagating over time. Each model trades off between performance and accuracy. For critical financial systems, strong consistency may be required. For social media, eventual consistency suffices. Understanding these models helps match architectures to requirements. Exam questions may test whether you recognize which model applies in a given scenario. Snapshots, replicas, and backups are related but distinct. A snapshot captures the state of data at a point in time, often used for quick recovery. A replica is a live copy, synchronized to provide redundancy. A backup is a long-term stored copy, often held offline or in different regions for resilience. Confusing these terms can cause operational gaps. For CCSP candidates, fluency in these distinctions ensures precise answers when exam items test disaster recovery strategies. Recovery Time Objective, or RTO, defines the maximum acceptable downtime for a service before it impacts business continuity. Recovery Point Objective, or RPO, defines how much data loss is acceptable, measured in time. For example, an RPO of 1 hour means you can tolerate losing up to 1 hour of data. Together, RTO and RPO drive planning for backup and recovery solutions. They anchor resilience in business priorities, not just technical capabilities. On the exam, RTO and RPO definitions help you evaluate trade-offs between cost, speed, and risk. Write once read many, or ORM. Storage enforces immutability. Once data is written, it cannot be modified or deleted until a set retention period expires. This protects against tampering, accidental changes, or malicious alterations. It is particularly valuable in compliance contexts, such as financial records. Immutability creates assurance that records remain trustworthy. For CCSP learners, WORM signals scenarios where compliance and evidentiary integrity are paramount. Key management underpins data protection. Services like Key Management Service, KMS, automate key lifecycle management, while hardware security modules, HSMs, provide tamper-resistant environments for generating and storing keys. Good key management includes generation, distribution, rotation, and revocation. Mismanaging keys undermines encryption, no matter how strong the algorithm. For exam questions, references to KMS or HSM highlight consumer responsibilities and the need for integration with governance frameworks. Data encryption states are defined as at rest, in transit, and in use. Encryption at rest protects stored data, encryption in transit secures data moving across networks, and encryption in use still emerging protects data while being processed. Each state addresses different risks, and together they form comprehensive protection. Exam questions may test whether you can distinguish these states and apply appropriate controls. Tokenization and format-preserving encryption are methods for protecting data fields. Tokenization replaces sensitive values with non-sensitive equivalents, while storing the real values in a secure vault. Format-preserving encryption encrypts data while maintaining its original format, such as credit card numbers. Both enable systems to function while reducing exposure of sensitive data. For CCSP preparation, these terms highlight field-level protection techniques, especially in compliance-driven industries. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Data masking, redaction, and de-identification are techniques that reduce exposure of sensitive information while still allowing certain uses. Masking replaces values with altered but realistic substitutes, such as turning a credit card number into a partially obscured version for training environments. Redaction removes or blacks out sensitive portions altogether, common in documents shared publicly. De-identification removes or alters personal identifiers to reduce the likelihood of linking data back to individuals, an approach often used in healthcare research. Each method balances utility with protection. Masked data can still support testing, redacted data can be safely distributed, and de-identified data enables analysis without revealing identities. On the exam, these terms distinguish different ways to minimize data risk depending on context and compliance requirements. Data loss prevention, or DLP, encompasses capabilities that monitor, detect, and prevent unauthorized movement of sensitive data. DLP tools may scan email, monitor endpoints, or enforce policies at network gateways. Policies can block actions, alert administrators, or apply encryption automatically. For example, DLP might prevent a user from emailing unencrypted medical records outside the organization. The goal is not only technical enforcement, but also reinforcing governance, ensuring that classified data is handled in line with policy. For CCSP candidates, DLP represents an intersection of technology, compliance, and human behavior, showing how policy translates into automated controls in cloud and hybrid environments. Access control models define how permissions are managed. Role-based access control, or RBAC, assigns permissions to roles which are then granted to users. Attribute-based access control, or ABAC, evaluates attributes such as time of day, device, or user department to make dynamic decisions. Mandatory access control, or MAC, uses labels and clearances to enforce strict, system-enforced rules, common in government and military settings. Discretionary access control, or DAC, gives owners discretion over access to their resources. Each model reflects different priorities: simplicity, flexibility, strictness, or ownership. On the exam, recognizing these models ensures you can align scenarios with the correct control approach, linking theory to organizational needs. The principles of least privilege and separation of duties complement access models. Least privilege means users and systems receive only the minimum access required to perform tasks. This limits damage if credentials are compromised. Separation of duties prevents one individual from holding conflicting powers, such as both creating and approving financial transactions. These principles reduce the risk of fraud, error, or misuse. They are simple in concept but profound in impact, representing cornerstones of security governance. In exam questions, references to access principles often highlight the need to reduce risk by limiting or dividing powers appropriately. Secrets management addresses how credentials, keys, and tokens are stored and rotated. Hard-coding passwords in code or leaving keys in configuration files is a common risk. Proper secrets management uses vaults, automated rotation, and restricted access. Rotation ensures that even if a secret is exposed, its usefulness is temporary. For professionals, secrets management embodies the principle of treating credentials as sensitive data requiring its own protection lifecycle. In exam terms, it emphasizes the consumer's responsibility within the shared responsibility model, especially in IaaS and PaaS contexts. Configuration baselines and golden images provide standardization for platform builds. A baseline defines expected configurations, such as required patches or disabled services. A golden image is a pre-configured virtual machine or container template that embodies that baseline. Using them ensures consistency, reduces misconfigurations, and speeds deployment. For security, it also allows for auditing. Deviations from the baseline signal risk. On the exam, these terms highlight the role of consistency and automation in reducing vulnerability from drift or ad hoc changes. Patch management, vulnerability scanning, and remediation cadence form the operational backbone of platform security. Patch management ensures software and firmware are updated against known flaws. Vulnerability scanning identifies exposures before they are exploited. Remediation cadence describes how quickly issues are resolved, often measured against severity levels or service level commitments. This trio reflects the never-ending cycle of discovering, fixing, and verifying. Exam questions may emphasize the governance side. Are patches applied within organizational policies? Are scans frequent enough to match risk? Recognizing these cycles underscores the link between operations and security posture. Secure boot, measured boot, and attestation focus on platform integrity. Secure boot ensures that only trusted, signed code runs when a system starts. Measured boot goes further by recording the state of each component, enabling verification. Attestation provides evidence to external systems that the platform is in a trusted state. Together, these prevent tampering below the operating system, such as rootkits. In exam contexts, these terms emphasize hardware and firmware protections that underpin trust in higher-level services. They remind you that cloud security begins not only with software but also with the integrity of the platform itself. Control plane telemetry captures administrative and configuration activities. This includes audit logs showing who created, modified, or deleted resources and when. Data plane telemetry records actual resource interactions, such as data reads and writes. Distinguishing the two is critical. The control plane shows governance activity, while the data plane shows operational use. Security professionals must monitor both to detect misuse, misconfiguration, or compromise. Exam questions may probe whether you can align telemetry types with the right visibility needs, highlighting the importance of logging and monitoring in cloud-native systems. Cloud Security Posture Management, or CSPM, automates the continuous assessment of configurations against policies and standards. These tools scan environments for misconfigurations, such as open storage buckets or excessive permissions, and often suggest or enforce remediation. CSPM reflects the need for scale. In large cloud environments, manual checks are impossible. For exam purposes, CSPM is a reminder that automation is essential for governance at scale. It shows how continuous oversight can reduce the risk of drift away from secure baselines. Zero Trust Architecture, or ZTA, is a model built on the assumption of breach. Instead of trusting users or systems based on location or network placement, every access request must be verified. This often involves strong identity, continuous authentication, and context-aware policies. The principle is never trust, always verify. Zero trust aligns well with cloud, where perimeters are porous and users connect from diverse devices and locations. On the exam, ZTA scenarios emphasize modern security thinking, where defenses adapt dynamically rather than relying on static boundaries. Service level agreements, or SLAs, define commitments between providers and consumers. Service level objectives, or SLOs, are the measurable goals, and service level indicators, or SLIs, are the metrics used to track them. For example, an SLA might promise 99.9% uptime. The SLO would define that target, and the SLI would measure actual uptime. Understanding these terms ensures clarity in expectations and accountability. Exam questions may use SLA-related terminology to test whether you can connect contractual obligations with operational performance. Business continuity and disaster recovery planning ensure data and platforms remain available even under disruption. Business continuity focuses on maintaining essential operations, while disaster recovery details how to restore systems after an incident. Together, they rely on concepts like RTO and RPO tested earlier. In practice, they integrate technical strategies such as backups and failover with organizational processes like communication and role assignments. In exam scenarios, these terms emphasize holistic resilience, blending technical and governance measures. Chain of custody refers to the documented control of data or evidence from creation through handling. In platform forensics, maintaining chain of custody ensures that logs or system images remain admissible in investigations. Evidentiary integrity requires demonstrating that no tampering occurred and that each transfer of control is recorded. This is not only a legal concept but a professional one, reinforcing trust in analysis and reporting. On the exam, chain of custody references highlight the governance dimension of incident response, showing that evidence must be managed with as much care as data itself. In summary, mastering data and platform terminology creates a shared language for classification, protection, and resilient operations. From lifecycle to access models, from encryption to zero trust, these terms form the scaffolding for both exam reasoning and professional collaboration. With precise vocabulary, you can interpret scenarios correctly, design controls accurately, and coordinate effectively across teams. For CCSP preparation, this glossary ensures that your knowledge is not only broad, but also exact, ready to be applied under exam conditions and in real-world leadership. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.